Hello, this is the third part of section 9.7, and with this part we're going to start looking at some applications involving solving logarithmic and exponential equations. So we're going to talk about compound interest problems in this section. So the compound interest formula is the following formula, and each of these letters have special meanings, so if you haven't seen it before, I want to briefly go through what each of them means. The A actually represents the amount in the account after a certain time t. The P stands for principal, which represents the starting amount that you might have in your account. The R is the annual or yearly interest rate, and when we use it in this formula, you always want to make sure that it is in decimal form. The N here represents the number of compoundings per year, or the number of times that you compound every single year. And then finally, the T in these problems is always going to represent the time in years. So there's a couple of things that you want to really keep in mind. The interest rate, R, is always in decimal form, and the time is always in years. Those are two things that are distinct to compound interest. You might wonder about how the problem is set up here. Now, the reason we divide the rate by the number of compoundings is because you need to spread out the interest rate over the year. And so by dividing by the number of compoundings per year, it's going to do that. Likewise, if you're compounding it more than once a year, you need to multiply the time or the number of years by those compoundings, because you're going to see several calculations of that over time. So let's look at an example that involves this formula. So the question we have here is, how long would it take a $3,000 investment to grow to $4,500 if it is invested at 8% compounded quarterly? And we want to round our answer to the nearest tenth of a year here. Now, if we take a look at the problem, we know that it is a compound interest formula because it's telling me we're compounding quarterly. Anytime you are given a certain number of compoundings, you are going to want to use the formula we have here. Now, if you're not familiar with this formula very much, then you may want to start by always first writing the formula down. Get comfortable with it because you will want to know the formula. So I'm going to jot it down here again for us. So now I need to look at the information that I'm given and see where it goes. The question is, how long? So this basically tells me I'm going to be looking for t. So t is the one variable here that I'm not going to have anything go into. Now I want to have a $3,000 investment. Well, that represents my P. So I'm going to put 3,000 in for P. That's what the money I'm putting into the account. That's my principal. And I want it to grow to 4,500. Well, that's my A. That's how much I want to have after a certain length of time. And then I have 1 plus the interest rate. There's my interest rate, and again, written as a decimal, 0.08. And compounded quarterly, quarterly means 4 times per year. So I need to divide that by 4 and then raise it to 4 times t. Again, the number of compoundings, which is 4, times the t. And I now have an exponential equation to solve. So guess what? I'm probably going to need to use a log at some point. But before I do that, I want to make sure that I isolate what's being raised to that variable exponent here. So I'm going to start by recognizing I have a number times all of this raised to that exponent, and I want to divide this by 3,000. And when I divide it by 3,000, this is actually going to divide in evenly as 1.5. And so I'm going to go ahead and always make sure that I have a nice exact number there. So 1.5 is now equal to 1 plus 0.08 divided by 4 raised to 4t. Well, it would be a little bit easier if I also could simplify what's inside the parentheses, and you could even use your calculator to do that if need be. But that simplifies down to a 1.02, and so now I've got 1.5 equals 1.02 raised to the 4t. So how do I go about solving that? Well, if I want to move that variable out of the exponent, I need to take the log of both sides. We've talked about that before. So I take log of 1.5 is equal to log of 1.02 raised to the 4t. And that's going to allow me to, again, bring that 4t to the front. So I have log of 1.5 is equal to 4t log of 1.02. Remember that these are all being multiplied, and you've got 4 times t times the value log of 1.02, and we're going to divide both sides here by 4 log of 1.02. All right. Now the last thing that I need to do here is I need to be able to come up with the numerical value here. In this problem, it doesn't make sense to tell someone, well, I need to leave my money in the bank for log 1.5 over 4 log 1.02 years. That doesn't mean anything to most people. So again, with applications, it makes sense to come up with the approximate value. So we're going to compute this. And so if we pull up our calculator here, we do want to be careful how we're entering this in. So the use of parentheses is going to be important. So if I'm going to evaluate log of 1.5, now the calculator does view that as a single number. I'm going to divide by, but now that 4 log of 1.02, I need to make sure I put it in parentheses in order for that to be done correctly. So 4, and I can just write log, it will understand that as 4 times 1.02. And now notice I need to close off the log, and I need to close off the denominator. And so that should now give me the correct result. And so I get this decimal representation of 5.12. Now, if I look back at the problem and what I was asked to do in the problem, it did ask me to actually round it to the nearest tenth of a year. So my final answer here would be 5.1 years. So always go back and double check the directions to see what your final answer should be. So this is one type of interest problem that you could work. Now there is another interest formula that comes out of the compound interest formula. Now remember, this one here is going to always be used when you know the number of compoundings. But what happens if you compound a lot? Say you did it daily or hourly or even by the minute or second. Eventually, you're going to be doing this so often that we come up with something that we call actually continuous compound interest. And so there's a formula for that as well. And you'll notice that a lot of the stuff that was in our other formula kind of gets condensed here. We still have an A, a P, but now we have E, and again that is our base that we use quite frequently with exponentials, and we know that that is actually a number. And so the information here is still going to be the same as what we did in the last problem. A is still the amount in the account at time t. P is still the principal or starting amount. R is still your interest rate in decimal form, and T is still your time in years. But notice that both the R and the T are in the exponent in this particular formula. One way that a lot of students will remember this is they'll think of it as the PERT formula. So if you're familiar with PERT shampoo, you can think about washing your hair when you're looking at this formula. Now, let's take a look at an example with this. Now, this example should look a little bit familiar because it's basically the example we did in the last problem. But now it says, how long would it take a $3,000 investment to go to $4,500 if it is compounded continuously? So as soon as you see this word continuously, that is when you can use this formula, and only then. If any length of time was given here, even if this said compounded hourly, we would want to use the formula we just looked at in the last example. So let's see what happens with this particular formula. A equals PE raised to the RT. So again, 3,000 goes into the P value. We have E, which is a number, raised to the R, which is 0.08. And again, we're still asking the question how long. So I'm still looking for T. And I'm looking for when does it equal $4,500. All right, so much like the last problem, notice that there's my base being raised to an exponent. So what I need to start to do with this problem here is get rid of that 3,000 first. So the start is going to look exactly like the last problem. And so 4,500 divided by 3,000 is 1.5, and that's equal to E to the 0.08t. And this is where it's going to get just a little bit different. Notice that I'm using the base E here. And so whenever I see the base E, instead of using the common log to solve, I'm going to choose to use the natural log here. So natural log of 1.5 is equal to the natural log of E to the 0.08t. This allows me to shortcut the problem a little bit because you might recall our little property that we looked at earlier in the chapter that says if you have the natural log of E raised to some exponent, it's always going to equal that exponent. So if you remember that property, you'll recognize that this is going to become just 0.08t. So 0.08t is equal to natural log of 1.5, and if I divide both sides by 0.08, I actually get to my answer just a little bit more quickly. So T is approximately, so let's pull up our calculator here again and see what we come up with. So notice, remember when we did it with the other formula, we had 5.1188. Well, now if I take the natural log of 1.5 and I divide that by 0.08, again, make sure you're closing off this parenthesis to get the right answer, and hit enter, it's now going to take not quite so long. It's approximately 5.07. And so notice the difference in those two numbers. When you compound continuously, it's not going to take quite as long to get the amount of money. So there is a benefit to continuous compound interest. And that's why a lot of people like to have retirement accounts when they're younger, because if you're compounding the interest, it's going to grow more rapidly throughout your lifetime. All right. However, if you take a look at, if we were going to round this to the nearest tenth, notice that this would also be 5.1 years. So there's not a major difference between these two, but I think you can see if we had gone for a longer length of time, you would have a very big difference between the two. All right, I have one final example that I want to take a look at, and that's this one right here. How long would it take 3,500 to double if it was invested at 8.75% compounded quarterly? So with this one, the key thing that's a little bit different from the other ones that we looked at is the fact that you have this word double in here. You're not given two numbers, and yet the setup is going to be very similar to what we did in our last couple of examples. But before we decide how to approach this, look at how it's compounded. It's compounded quarterly. Which formula do I use? Do I use the compound interest formula, or do I use the continuous compound interest formula? Well, as soon as I see this quarterly here, I know that the formula I must use is A equals P times 1 plus R over N raised to the NT. I do need to use the compound interest formula. Now, 3,500 is my starting amount. And let's see, I've got 1 plus 0.0875 divided by, and I'm doing this quarterly, so I divide that by 4, and I raise that to the 4t. Now the question is, what's my A amount? Well, this is where the word double comes into play. I want this amount to double. So twice 3,500 is 7,000. And so when I go to solve this equation, notice that if I divide both sides by 3,500, I end up with 2 is equal to, and again, if we can simplify this number down, we're going to go ahead and do that. Now, that might not work real nicely on this problem. Let's see what happens. 1 plus 0.0875 divided by 4. What's that going to give me? Well, it's a big long decimal, and at this point it's very important that I maintain all those decimal places so that my final answer is more accurate. So you have the choice of leaving it in this form or using the decimal representation form. I'm going to choose to leave it as 1 plus 0.0875 divided by 4 raised to the 4t. Now on this one I'm going to use the common log. I could also use the natural log, but my choice here is to use the common log. And I'm going to take the log of both sides. And again, by doing that, I'm able to now bring that to the front. So I have log of 2 is equal to 4t times log of 1 plus 0.0875 divided by 4. And I still do the same thing I did in the first example. I divide both sides by 4. And since I'm going to use a calculator, this ugly number here shouldn't scare me at all. Divide both sides. And the final step is to just calculate this. And I'm going to get an approximate answer. I already know that. So I'm going to come over here and compute this into the calculator. Let's clear the screen. And I'm going to look at log of 2 divided by, again, remember to put this in parentheses, 4 log of, and now I'm going to enter in this calculation, 1 plus 0.0875 divided by 4. Close off the log and close off the denominator. And when I hit enter, I get 8.00, or very, very close to 8 years. So that's the final example that I wanted to show you here that involves compound interest. So again, you'll be looking at some different problems with this in your homework.